In physics, most of the functions we study are either exponentials or power laws. These functions can look pretty similar on a graph of data, but they behave very differently. One way we can clearly identify these different functions is by using logarithmic axes. When using logarithmic axes, the trick is to think in terms of a new x and a new y. For an exponential function, your new x is the same as the original independent variable, but the new y is the log of the dependent variable. This allows you to cancel the exponential part of the function, and you get a linear function instead. Note that the slope of this new linear function is whatever multiplied x in the exponent. For a power law function, your new x is the log of the original independent variable, and the new y is the log of the dependent variable. This allows you to separate the independent variable from its power, and you get a linear function instead. Note that the slope of this new linear function is the power x was raised to. Now we'll look at how we can implement this practice in VPython. We'll start by defining all of the constant factors in our function. So here we've got the two constants that appear in the exponential relationship: a, the number that multiplies e out front here, and b, the number that multiplies x up in the exponent. These are the 2 degrees of freedom you have in an exponential function. And then we've got the c and p that we have for a power law. So we've got the coefficient out in front that just determines, how large it is. And then we've got the power p that determines how fast it grows or dies down. We're going to graph both these functions on the same graph. Here we've created this thing, my graph. We're going to start out with just linear scales. So the way you control a log versus a linear scale in VPython is with these log x and log y arguments. So a log x or log y of false means you are using a linear scale. If we set it to true, then we're going to use a logarithmic scale. And here we're keeping track of our two functions. We're going to graph the first one in red and the second one in blue. And I'm not going to worry about which one is red and which one is blue right now, because we're going to use the log-log scales to figure out which one is which. And here we're creating our data to be able to graph. So this is just a simple for loop. So we're looping over values of x between 1 and 50 in steps of 0.1. So we'll have lots of data points to look at. Our first function we've got here is our exponential function. Remember, it's called exponential because x is in the exponent. And then here we graph our power law function. It's called a power law because x is being raised to a power. So if I hit Control 2 and run this, I get both functions, and you see they're both growing. They've both got some curvature to them. And if I were just looking at these two curves here, I wouldn't really be able to tell which one's the power law and which one is the exponential, because I could, stretch and expand these things to get them to take on some slightly different shapes to kind of match each other. If I got out a ruler and started, measuring the rate of change at each point, I could technically tell it, but I can't tell it just by looking at it. And so the benefit that we gain from using log scales is that we can tell visually right away which one is definitely a power law, which one is definitely an exponential, or whether the function is something completely different. So let's try out the first scenario. So we saw earlier that if we set the log y scale equal to true, so if we set the y-axis to be a logarithmic scale, then this exponential function should become a line, and this power law will not become a line. Now, if I just run this as it is, VPython doesn't know what I want my window to look like, so it kind of pushes all the data up to here because it's got a minimum value of 0 for y down here, and that's causing some problems up here. So we need to add in a y minimum and a y maximum, so I just happen to have made a note to myself to do that right here, so I can get rid of that little note. So we're going to set a y min of 0.1 and y max of 10,000. We can adjust that if we need to, but I believe it turns out fine. Yeah, we can see both functions fine here. You can see that the red one makes a pretty clear straight line. So you notice that our y scale now has become a logarithmic scale. So basically what that means is that we are giving equal spacing to powers of y, or to powers of 10. So you can see that a little bit better if I increase the range. Let's increase this to 100,000. And basically what the log scale does is it means that going from 0.1 up to 1, so that's going up 1 power of 10, gets just as much space as going from 1 to 10. And that gets as much space going from 10 to 100. Where's 100? There's 100 about. And that gets the same amount of space going from 100 to 1,000. And that gets the same amount of space going from 1,000 to 10,000. Here, yeah, 1 times 10 to the 4. And then that gets as much space going from 10 to the 4 going up to 10 to the 5. So these decades, as we call them, each get an equal amount of space. And basically what that does is it flattens out the exponential at just the right rate so that it becomes a straight line. Now, our power law does not become a straight line because it's not an exponential. Graphing log versus linear only makes the exponential a straight line. It doesn't make the power law a straight line. If I want to make the power law a straight line, what I need to do is use a log scale instead of log linear. So I need to make this log x equal to true. This is going to do the same kind of squishing we have over here on the x-axis. Again, the same amount of space is given from 0.1 to 1. Oh, I'm looking at the wrong. I was wondering why it wasn't changing. I was looking at the wrong thing. It's giving the same amount of space from 1 up to 10 and from 10 up to 100 off the graph over here. And what you notice is that this time our blue dots form a straight line. So now we've got our power law forming a straight line, while our exponential doesn't form a straight line. The red curve was fine being a straight line as long as we had a log on the vertical and linear on the horizontal. The horizontal axis is scrunching up too fast for it to be a straight line, but it's scrunching up just fast enough for the power law to turn into a straight line. So that's one of the primary ways we use log scales, is to identify power laws versus exponentials. Another useful trick for a log scale is looking at features that occur at very small orders of magnitude. So for example, suppose I also wanted to look at the function e to the negative x squared. This is a pretty popular function. This is the Gaussian distribution. Let's make a third set of my dots here. Do my dots 3. And that means I just need to add one here. So this is a neat function. Let me show you why in just a second. We'll graph it on linear scale first. Let's make it green. Let's make these both linear for right now. So let's set this false. Let's set this to be false. Oh, right. I need to adjust my scales there. There we go. And let's also comment out these two just so we can view just this function. Control 2 to run. So you notice that this thing, it flattens out pretty quickly and then it goes up to this peak. And then if I graph it on the negative side, it has to come back down since it's an even function, which means it's got a maximum somewhere in there. If I want to get a better look at that maximum, I have to turn my log x into true. So I have to turn my x scale into a logarithmic scale. I'm still not quite seeing where the maximum levels out. So let's actually go lower in terms of where x starts. Let's go with a 0.01. Let's make this go in steps of 0.0001, and let's only have this go out to 10. Control 2 to run. And so thanks to this log scale on the x now, I can better see this flattening out as I get up toward the maximum, because normally this would get scrunched in on a linear scale within this 0.1 once I get too far past this space. So this just allows me to see a maximum like this, a nice small scale feature like this, which is pretty important because I might need to know what the width of this exponential peak is. So that's a primer on how you use log scales in VPython. They're pretty handy in research. I hope you enjoy using them. Thank you so much for watching. I will see you next time. Bye-bye.